What is the dimension, proper way to define the dimension of the map A inverse, which is the product of three maps, B, C, and D? This question really seeks to find a way we can represent A inverse, which is B times C times D inverse, in terms of, so to be something that involves B, C, and D. How do we do this? Now, this is a sign that, we're going to cook up something. This is what we're going to do now. And the key is to find the only way we can define this such that it makes sense. So we have three maps, B, C, and D. Each map has, some set of dimensions. Let's say this has M times N. This has P times Q. And this has R times S. Some dimensions. Then what does this mean? Again, we need to always remember how we like to conceptually understand the matrix. It is a map. We have reiterated this multiple times already, but more specifically, it is a map here. This B is a map that takes a vector of length m and outputs a vector of length n. Same thing you could say about C and D. So C takes an input of length p, and D takes an output of length s. Okay, so we would like to have this now in terms of B, C, and D. This involves the inverse. Then I think it is fair if we take a good look at the inverses for each map. So B is a map that takes M as input and outputs N. Now, what should the inverse map do? Yeah, of course, right? That's what I thought as well. So it outputs an m-dimensional vector, and it inputs an n-dimensional vector. It's the dual of the original map. So everything is reversed. This is the inverse. Now, I think it is now a good idea to try to see how we can properly define this. If we compose two maps, let's say we assume that the answer will be B inverse, C inverse. Let's assume this will be the answer. Let's say even D inverse. Maybe this is the answer, we don't know. How do we check this? Yes, the answer is very simple. You just follow the input and output sequence. So this inputs N, outputs M. This inputs Q. That's a problem, right? Because the output from here does not match the input. Then definitely with 100% probability, this is not going to be the case. But how do you know that M is not equal to Q? That is also another question. Is there something here that we still have not utilized just yet? Yes, I'm not sure if you noticed this already, but I hope you don't go rushing at the problem too hastily, because this will cause you some issues. This expression is defined, and this is what we haven't used just yet. I wasn't referring to our brains. I was just... You're good. You're a very smart person. I wasn't trying to offend you in any way possible. Just to make this clear. Anyway, this is It's a huge misunderstanding. So if this is defined, then the output of B, and perhaps I should write this down now, the output of B should match the input of C. So we said B is M times N, and C is P times Q. Then with 100% probability, this is defined, then I can tell you that N is equal to Q. Perhaps I'll even do this. I'll replace this P and I'll write N, because why wouldn't I do that? And with the same logic, D is, some R times S matrix. The output needs to match the input. So Q is, with 100% probability, equal to R. I could just write Q, because why not? So let me write this now. So what we did here is we started with M, we got to N, and then N, and then Q, and then Q, and then S. Now, how do we, continue on with this path? Is a good question. Now, think about this for a moment, and now let me go back here. So here we had N times M, this is the inverse, and now Q times P. So with 100% probability, the inputs don't match, that's for sure. Well then, what will match with M? Is there anything that will match with M? Not really. Then probably this should be, to the very right, because there's nothing that could match it. But if we look at this, for example, Q times, well, why did I write P? It's not P, it's N. They're exactly the same. If I look at this now, then this is great, because I can look at this product and I can make sure that it is well defined. Well, P is just equal to N. Then this is properly defined. And then it just remains to put the D inverse, which is S times Q. S is a bit isolated. There's nothing which is it is equal to. But do you see how this fits very nicely? Just like this, S times Q, Q times N, and N times N. This is really how it looks like. I hope the problem wasn't too snaky for you. This is really how you do it. And I even claim that this is the only way you could define the inverse matrix using the inverses of each matrix. And this is, of course, the case when you look at the product. This is, of course, what I mean. Perhaps for clarity, I'll review this now. So we had M times N, N times Q, and Q times S. Now it has become the absolute opposite. So everything gets reversed. You have this, and now it's in the other direction. And I think this makes sense for an inverse, because this is a map that takes an m-dimensional vector as input and outputs an s-dimensional one. The inverse matrix, as it should, takes an s-dimensional vector and outputs an m-dimensional vector. So I think this is very good for this exercise. And I think that as long as you think about maps as matrices and matrices as maps, then you will always have this conceptual understanding, which will help you greatly in such problems, and perhaps even other more problems to come. Then you wouldn't have to watch me for 10 minutes doing this video. And then I'll be very happy, because you're actually learning things. So I hope you are learning things by watching this tutorial.